welcome to this session. This session, we are going to do an example on trapezoidal rule. So the question is, there are two parts. Part A, to find the exact value of the integral dx over 1 plus x squared within the interval -1 to 1. Then number 2, for B, approximate the above integral using trapezoidal rule with 4 intervals, 6 intervals, 8 intervals, 10 intervals, 12 intervals. And then at each stage, we comment on the result by finding the errors and percentage errors of each value. Now, solution. So part A, evaluated from calculus. Integral from -1 to 1 dx of 1 plus x squared. We know that integral of 1 over 1 plus x squared is tan inverse of x. Now we apply limit from -1 to 1. So this would be tan inverse of 1 minus tan inverse of -1. And for you to get the correct value when you are putting in the limits here, ensure that the mode of your calculator is in radians. If your mode is in degrees, you'll get wrong answer. So ensure that your mode of the calculator is in radians. And when you work out tan inverse of 1 minus tan inverse of -1, the answer is 1.5. So tan inverse of 1 minus tan inverse -1. So you get 1 point 1.57 0.796.327. So that's what you get. And then, so that's the exact value. Or this is the same thing as saying 1/2 pi. So that's the answer to the first part. Part B. So using 4 intervals. So mean that we have to get h, which is given by b minus a divided by n. So n is 4. So we'll have 1 minus -1 divided by 4. So we'll get 2/4. So h is a half. So you make a table of values, x and the value of the function. So we are starting at -1 plus a half, you get -1/2, plus a half, you get 0, plus a half, you get a half, plus a half, you arrive at 1. And when you work out this, so remember the value when you are given integral from -1 to 1, dx over 1 plus x squared, then do the same thing as writing -1 to 1 1 over 1 plus x squared dx. And if you compare with the general integral a to b of f of x dx, then your f of x is this 1 over 1 plus x squared. So you put -1 into this one, and then you get the value of the function. It will be a half. Where there's x, you put -1/2 and evaluate. You'll get 4 over 5. When you put 0 here, you get 1. Put a half, you get 4 over 5. And then put 1, you get a half. And you know, by definition, integral is given by h over 2. That's by trapezoidal rule. H divided by 2 into, so this is our f0, f1, f2, f3, and f4. So the extremes will be f0 plus f4, and then plus twice the middle ordinates, f1 plus f2 plus f3. When you work out this, you'll find that integral, the integral will be given by, so h, a half divided by 2, you get 1 over 4. A half plus a half, 2 into 4 over 5 plus 1 plus 4 over 5. And when you input these values in the calculator, you'll get that that integral will be a quarter into a half plus a half is 1. This other part will give you 26 over 5. And when you work out this one, it will be 1 over 4 times 31 over 5. This will give you 31 over 20, which is 1.55. So error, because now we have to calculate the error at each stage. So error, let's call it E1, is given by exact minus approximate. And actually, we are just interested in the value of the error without the sign, so with absolute signs. So we'll have exact is a half pi minus approximate is 1.55. This will give us 0.02079632679. Please don't round off any value so that you don't introduce errors in the calculation. So percentage error is always given by error over the true value, which is 1 over pi times 100%. And when you do that one, you get the answer to be 1.323935283%. Please confirm that solution. And then part 2, we were to use 6 strips. So which means our H will be B minus A over N, 1 minus minus 1 over 6, which is 2 over 6, which is a third. So you make a table of values, X, and then the value of the function F. So we have -1. When you add a third, you get -2 over 3. Add a third, you get 0. Or you get negative a third. Add a third, you get 0. And then 1 over 3. And then we have 2 over 3. And then we have 1. So this will give us a half. This is 9 over 13. This is 9 over 10. This is 1, 9 over 10. This is 9 over 13. And this is a half. So this is our F. Remember, you are using F of X is 1 over 1 plus X squared. So when you input in these values of X is what generates these values I'm writing here. This F0, F1, F2, F3, F4, F5, and this other one is F6. So by trapezoidal rule, I is h over 2 into the extremes, we'll have f0 plus f6 plus 2 into f1 plus f2 plus f3 plus f4 plus f5, and then close. When I'm putting, so my h is a third, dividing by 2 is 1 over 6, so I'll have 1 over 6 into a half plus a half plus 2 into 9 over 13 plus 9 over 10 plus 1 plus 9 over 10 plus 9 over 13. When you work out this, you'll get a half, 1 over 6 1 plus 544 over 65. And please, when you are doing such calculations, ensure that you don't do any rounding off. It's always good to put the values in fractions so that you are dealing with the exact values. So we'll have 1 over 6 times, when you add this, you get 609 over 65, which will be 203 over 130. And you can put in decimal, it is 1.56, 1538462. So error, let's call it E2, will be given by, for the fruit error, exact value, which is a half pi minus this approximate 203 over 130. This will give us 9.257865256 10 raised to negative 3. So you see, by increasing the number of intervals, we have reduced the value of the error. If you compare this error and what you got in the first case as 0.02, because when you write, if you write this one in decimal, it will be 0.009, and then 257865256. So this is smaller than the previous one, we got 0.02. So percentage error will be error we are getting here divided by the exact value multiplied by 100%. And when you do that one, you get 0.5893740072%. Compared to the previous one, which was 1.32, then you see that this is also smaller. So by increasing the number of intervals, we are reducing the number or the size of the error. Part 3, n equals to 8. So h will be 1 minus 1 over 8. So 2 over 8, which is 1 over 4. So we'll have, you make a table of values, x, and then the function. So we have -1. When you add 1 over 4, you get -3 over 4. Add a quarter, you get -1/2. Add a quarter, you get -1/4. Add a quarter, you get 0. Add a quarter, you get 1 over 4. Next will be 1/2. Next will be 3 over 4. And next will be 1. So this will be 1/2. When you work out, this one will be 16 over 25. This other one will be 4 over 5. This one will be 16 over 17. This one is 1, 16 over 17, 4 over 5, 16 over 25, and then 1/2. Once you have gotten the values, don't forget that these values are generated from f of x equals to 1 over 1 plus x squared by inputting the values of x. So this is your f0, f1, f2, f3, f4, f5, f6, f7, f8. So integral is approximated by h over 2 into f0 plus f8, those are the extremes, plus twice the middle ordinates, f1, f2, f3, f4, f5, f6, and then f7. So a quarter divided by 2 is 1 over 8. So we'll have the integral I is 1 over 8, a half plus a half, plus twice. This other one is 16 over 25, plus 4 over 25, 4 over 5, and then plus 16 over 17, plus 1, plus 16 over 17, plus 4 over 5, plus 16 over 25, plus, okay, so that's the last one. It's 5. So when you work out this, will be I equals to 1 over 8 into 1 plus the sum of this one, I'm multiplying by 2, you get 48, 98 divided by 425. It is always good, unless it's impossible, express your answers in fractions so that you get exact values. If you put in decimals and round off some values, you'll be introducing errors in your calculation. You have 1 over 8 times 53, 23 over 425. This one, when you work out, you get 1.5, 6, 5, 5, 8, 8, 2, 3, 5. Now error, let's call it E3, will be the absolute of the exact, which is a half pi minus this value. I get this difference, you get 5.208091501 times 10 base power -3. And then percentage error will be this error E3 divided by the exact value times 100%. This will give you 0.33155,740.26%. When you compare this percentage error and the previous one when n was 6, you see that still it is now lower than the previous one. And even the error at this point is less than the error in the previous one. So the same pattern, as we increase the number of n, then the value of the error in our calculation is reducing. The second last one, we have n equals to 10. So h will be 1 minus 1 over 10, which is 2 over 10. Now this is 1 over 5. Now you make a table of values, x and then f. So -1, adding 1 over 5 to get -4 over 5. Next will be and then -1 over 5, 0, 1 over 5, and then 2 over 5, and then 3 over 5, and then 4 over 5, then 1. So we have a half, 25 over 41, 25 over 34, 25 over 29. Next one is 25 over 26, 25 over 26, and then 1, 25 over 26, and then 25 over 30 over 29, 25 over 34, 25 over 41, and then a half. Please, you get correct values if you avoid rounding off, and that will be better if you write your values in terms of fractions. So this is F1, this F0, F1, F2, F3, F4, F5, F6, F7, F8, F9, and F10. So we know that integral is h over 2 into, so F0 plus F10, and then plus twice F1 plus F2 up to plus F9. Now we say I equals to h, so 1 over 5 divided by 2 is 1 over 10 into a half plus a half plus twice, then 25 over 41 plus 25 over 34 plus 25 over 29 plus all the way up to the value of F9 is 25 over 41. Please add all these values I've not written here. When you work out this, you get 1 over 10 into 1 plus twice all this sum. You should get 14.67463057. And when you multiply by 10, you get 1.56746305.7. And then error, let's call E4, will be given by a half pi this will give you 3.3332695 times 10 raised to the power negative 3. And percentage error will be this error divided by the true value times the 100%, and you get 0.21220. So which shows that still the error as compared from the previous one, it was 0.33%, here is 0.21%. So it's still smaller than the previous one. And lastly, N12 means H will be 1 minus 1 over 12. So 2 over 12, which is 1 over 6. So make a table of values, X and F. So -1 plus 1 over 6 is minus 5 over 6, plus 1 over 6 is minus 2 over 3, and then plus minus a half. Next will be minus a third. Next is minus 1 over 6. Next is 0. Next is 1 over 6. Next is a third. Next is a half. Next is 2 over 3. Next is 5 over 6. And lastly, 1. So this is a half. That's 6 over 61. And then 9 over 13. 4 over 5. 9 over 10. That's 6 over 37. And then 1. And then that's 6 over 37. And then 9 over 10. 4 over 5. 9 over 13. That's 6 over 61. And then 1. 1 over 2. So this, you call it F0, F1, F2, F3, F4, F5, F6, F7, F8, F9, F10, F11, and F12. So I is H over 2, F0 plus F12 plus twice F1 plus F2 plus F3 up to plus F10, and then lastly F11. Now H is 1 over 6. When you divide by 2, it will be 1 over 12. So I'll have I 1 over 12 into a half plus a half plus twice into 36 over 61 plus 9 over 13 plus 4 over 5 all the way 4 over 5 plus 9 over 13 plus 6 over 61. Please include all those values to get the correct sum. And when you work out, you get a half, a 1 over 12 into 1 plus the other part will give you 17.8217784, which when you multiply, you get 1.568481.533. Now error, say E5, is exact, which is a half pi minus this approximate 1.568481.533. When you work out this one, you get 2.314793559 times 10 raised to the power negative 3. Percentage error is this error over the correct value times 100%. When you work out this one, you get 0.147364334.9%, which is also less than the previous one, which was 0.212%. So this trend is always true in general. So the last comment we say, then the more the number of sub-intervals, the less the error and the better the approximation. So this is the same thing as saying that when the width h is made smaller, we get a better accuracy, or the result has less errors. So that's the thing. So if you reduce the number of size or increase the number of subintervals, then you get a better approximation. But then the disadvantage will be the more you make the width smaller, the more computations you have to do. But then that's what results into better approximation. Thank you.